Alright, I want to do a little bit with volumes with known cross sections. And so there's kind of two different versions up here of the general formula. V stands for volume, and it's going to be an integral from A to B, which in this instance, A would be here, B would be here. And in this instance, A would be down here and B would be here, because we're in terms of X and Y. And then what is A? A of X is the area, that's why we use A, of whatever cross-section is defined. And what I mean by that is if you think of this fish-looking thing as the base, it's laying flat, the idea is you're building some volume coming off of the paper towards your face. So I can't really draw it in 3D, but like if the cross-section was a square, these squares would be coming up towards you. But this distance that I'm highlighting would be the length of one of the sides of the square. And if it's truly a square, then it would be coming off of your paper, coming off the screen at the same height. But as you create these cross-sections, the dimensions of the square, whatever you're trying to create, they change. So I'm going to do a couple examples to try to describe this, because it is kind of an abstract idea. But whatever the area is of your cross-section, that's the kind of the formula that you're going to use. The reason we did a bunch with, pi r squared, specifically with the disk method, is because when you rotate a curve, you have a bunch of circles. And that's the area of a circle. Now we're going to look at cross-sections that aren't circles, other geometric shapes. All right, here we go. So these are a couple problems off the handout, and please stop the video if you haven't attempted these on your own. This is just for you guys to check your answers, but please try them on your own. So we're going to try to come up with a volume of a solid that's bounded by x squared minus 6x. So let's just jump right into it. If I was just doing this by hand, I would factor it. And what happens is I get an intercept of 0 and an intercept of 6. That means that the axis of symmetry is right through 3. And if I plug in 3, it looks like I get a negative 9. So it says that it's bounded by this and the x-axis. So I think I'm going to have like a parabola here. And the base that I'm trying to create for this weird object is the perimeter of this. Bounded means that this is the boundary. Cross sections are isosceles right triangles. So just a reminder, that's a right triangle where the two sides, we'll call it S, are the same length, are placed parallel to the y-axis. All right, so I would draw this in as you go. So this is parallel to the y-axis. Kind of looks like an ironing board or something to me. I shouldn't say board, iron. And what's happening is these triangles are they're coming up off. Again, I can't draw it straight up in the air. It should be a 90-degree angle, but they're coming off of the screen, towards your nose. And the idea is we're trying to add up all of those to create some weird-looking shape. When it says perpendicular to the base, this means it's a 90-degree angle coming off of the paper. So again, that's very hard to draw, but the real thing is that these cross-sections, the way I'm drawing right now, these are parallel to the y-axis. That's telling us that we're going to use dx, these little thicknesses. So how's the structure of this work? General formula is I need the area of the cross-section. It looks like I'm going to go from 0 to 6 because we're using x's. And what I really need is the area of a generic triangle. So really watch this part. Here's the key. I need this length. It's changing. So I need to represent it in terms of a function. So if you think about a sample point again, this right here is the y value. So I believe you can this length as y. But that means this length is y, because it's an isosceles right triangle. So the area would be the area of this triangle. 1/2 base times height. If it was a square, it would just be y times y. This is like a square cut in half. So I'm going to take this discovery. How am I doing on time? I'm doing okay. And I'm going to plug that in right here. So it's a similar game that we've played before, in that we got dx and we got a y, and then that's where this comes in. So what do we got? We got 0 to 6. I can pull out the 1/2 if I want. Y is this. And that integral should give the volume of this object that we created using the scenario above. All right, you can pause it and kind of regroup, go back if you want, but let's look at another one. So number 5 on the same handout, it says a solid has a base bounded by a semicircle of radius 6. All right, so let's just kind of sketch in a semicircle. It's not much, but I can do better. So this is supposed to be 6 up here. Cross sections are semicircles perpendicular to the base, that means coming off the paper, and parallel to the x-axis. All right. So the idea is that these are my cross sections, but they're supposed to be semicircles coming off of, the paper. So you kind of have this almost like this dome type of thing, but the base is a semicircle itself. So I'm going to try to clean this up a tiny bit. I like to usually draw in the cross sections, but then what I do is I'll have a separate drawing or actually have this, and I want to find the area of this, in this case, the semicircle. So again, if I think of a sample point, it looks to me like the radius of all of these is just going to be x. Right? Whether you pick this semicircle, it'll always be x. So if I come up with the area of this semicircle, it's going to be 1/2 pi r squared. Again, this is the area of the cross section. So how is this going to work? Well, my formula here that I introduced, we got cross sections that look like this. So we're going to use dy. So this is dy, and that means this is going to go from 0 to 6. And I'm going to put my area formula in here. but we've got some substitution. And so this is where the other section comes in. We need an equation of the semicircle. And with a radius of 6, we'd have 6 squared here, which means we could say this is 36 minus y squared. So pause it if you didn't get this. Think about it for a second. I need to use this. So my volume, I believe, is going to be 0 to 6 of 1/2 pi x squared. But x squared is this. So there's a few options you have here. You know, you could go 0 to 6 and then just have 36 minus y squared. I pulled the 1/2 pi out. I'm supposed to get the pi out of there. And then you could do this by hand if you wanted to. Encouraging technology, but that's going to be the setup for this scenario. All right, let me just do one last little side problem with this. Let's say it's the exact same scenario. I'll change the color though. But let's say your cross sections were squares. So instead of having a semicircle, your cross section would be a square. So people struggle with this last chapter. What you know is that this length right here is x. That means this would be x. But since it's a square, you know, you'd have 2x over here. So if I said, what's the area of this square? I hope you would say, you know, 2x times 2x is 4x squared. So the integral would be almost the same, where you have 0 to 6 dy. But now the cross section is a square. So you'd plug that in. But again, you got the xy problem. So final answer, what would it look like if it was a square? You'd have 4 and then your x squared version. So again, this is kind of a made-up question on the fly because I had another minute or two. But that would be the integral for the volume created if your cross sections were squares. All right. Thanks for watching. Hopefully this helped a tiny bit. Again, stick with it. You guys are awesome. And thanks for watching.